Welcome back to the lab. Today we're going to implement soft start and overcurrent protection in our UPS. And we've talked about soft start a few times, and the principle is pretty simple. We want to transition from off to on slowly rather than as fast as possible. Implementing soft start in a traditional switch mode power supply will reduce inrush current and generally reduce stress on components in a design. Awesome stuff. Now, is this necessary for the output of a UPS or anything connected to mains for that matter? No, it's not. I'm betting that every single one of us has plugged things into a wall and flipped a light switch without a second thought. But you know what? If we're going to go through all the trouble of building a UPS, we may as well slowly ramp on the AC output because we can, and it feels good, okay? In all seriousness, there are more reasons than that one why I want to implement the soft start routine. A big part of this is safety or sanity checking. Technically, both halves of our UPS are generating voltage, even though we're really more interested in the voltage across the two outputs than either output itself. We've designed these outputs such that in the normal operating case, one is set to a positive voltage above the halfway point, the other one's set to a negative voltage below that halfway point. But they both have that DC offset of 1/2 our DC bus voltage. The way that our soft start routine works allows for detection of excessive current flowing from either output to ground before applying any differential voltage across those two outputs. And that's pretty critical. We can do this because of a very important design decision. Our UPS is capable of monitoring output current not on only one leg or one side of the output, but both. And normally, these two currents are always the same value, same magnitude, same sign. Usually, we're measuring the same thing twice. But it's when we are not getting the same value from both of those current sensors that we need to start asking some questions. Since we're measuring the current coming out of one half H bridge, and we're measuring the current circulating through the load and back into the other half of the H bridge, if there's current missing, where did it go? And this is fundamentally the idea behind a GFCI breaker. This won't really be GFCI, but we can set an absolute threshold for how much current mismatch is allowed before everything shuts down. That's a pretty good transition into our first topic. What kinds of overcurrent protection should we be thinking about for our UPS? 3 limits immediately come to mind. I think that we should be limiting the RMS output current. This one's pretty basic, and it prevents the UPS from becoming thermally overloaded. It's a very important limit. While we're at it, I think we should also limit the peak output current. And this will trigger the soft start routine if too much current is demanded by a downstream load, so we should probably set that pretty high above our regular operating current limit. This is mainly for short circuit protection on the output, and there might be some inrush currents that could trip it. We'll have to be careful. But this went from a nice to have feature to a we should really probably implement this feature after our recent control loop changes. Our recent change significantly improved stability, but our UPS is now only able to respond to voltage and current once every 25 milliseconds. This means we'll likely miss those little transient events, the inrush currents, the short circuit events. Well, at least we won't catch them for 25 milliseconds. And even when we do, if it's a transient event, that'll get averaged out with all the other data that we've been collecting over that 25 milliseconds. I think it would be a little more responsible to implement this transient peak current limit as an independent sanity check that kind of removes control from the control loop and shuts everything down, restarts the control loop, starts it up again. It should be a discontinuity to improve the transient response time to short circuit events. I want this thing to turn off as fast as possible. If we ignore a short circuit and keep the UPS trying to drive like everything's fine for 25 milliseconds, our inverter stage might blow, and it likely wouldn't blow the fuse. Fuses require a thermally significant time to open, since the failure mechanism is literally melting a wire. They don't do a great job of protecting against fast transients, but that's usually a good thing because nuisance trips in a fuse are annoying. The peak current limit will allow this UPS to detect and resolve those fault conditions in as little as a single millisecond. There's no guarantee that the inverter or UPS won't be damaged in that millisecond, but I'm guessing that by responding to this peak overcurrent by shutting down as soon as possible, we'll give it the best chance of survival, at least as good as we could. Don't go short-circuiting Don't go short-circuiting this the same way you wouldn't short-circuit mains. The leakage current limit is also very important. Like we said before, if there's current coming out of one half of the inverter and it's never coming back, it needs to be going somewhere. More likely than not, this current is leaking back to earth ground through, well, probably you, me, our dog chewing through the mains cord. I have no idea where the current's going, but it's probably best to shut down and figure out where that current's going later. This brings us back to that soft start routine. Routine that we implemented has 2 phases. Well, technically 3, but the third phase is just being on, so the first 2 are the most interesting. When transitioning from off to on, there are 2 things that need to happen. First, we need to bring the common mode DC voltage on both inverter outputs up to 1/2 the maximum DC voltage. Once that common mode base has been established, we can then ramp up the amplitude of our sine wave, and when turn on time and overcurrent hiccup time minimization becomes our primary concern, there's absolutely no reason why these 2 things can't happen simultaneously. However, to make our faults more obvious, we've separated these 2 tasks to happen sequentially. Right after a user pushes the power button in the UPS, nothing happens. Well, a light blinks to acknowledge your input, but nothing else. This is the, "You sure, bro?" sanity check. Push that power button again, and things start to get interesting. Buzzing starts, things come to life, but most importantly, we enabled the DC to DC boost converter and fixed both inverter outputs to 50% duty cycle. This brings both legs of our UPS up to approximately 125 volts DC, and the voltage across them to approximately 0. Once here, we dwell for about a second, monitoring the leakage current, verifying that there's no excessive current draw from either leg to ground. Any current drawn now would be pretty weird and a serious fault, because there's no voltage across the output. There's 1 out of 3 safety checks. The next phase is where this UPS starts to output voltage. Rather than slamming the UPS on with a full amplitude AC pulse, inducing significant inrush current, we take things a little more slowly. Over the course of 4 to 5 half cycles, we provide a progressively increased amplitude on the output. This allows any downstream capacitors to charge a bit more, providing the opportunity for downstream loads to turn on a little more gracefully. Here's what that looks like on the scope. We don't have a good current probe on here right now, but you can see the voltage. Doesn't that just fill you with little warm fuzzy feelings? Look at the level of control we're able to achieve. Just look at it. When we want 10 volts AC on the output, we get it. When we want 50, we get it. All the way up to 120 volts. It's meant to be a triangular ramp, and if I hold my tongue at the right angle, it looks pretty triangular, but it's not really. When ramping this load on, we're constantly enforcing the instantaneous and RMS current limits, which means that if the UPS is overloaded while turning on, it'll probably cut out somewhere during that ramp from 0 to 120 volts, preventing browning out connected equipment for an extended period of time. There you go, that's 3 out of 3 checks. That's everything we wanted to implement. So every time the first or second soft start phase fails, we have a counter that runs, and we just add 1 to that counter. And we only reset that count of failed soft start attempts after getting through the soft start phases successfully. Once we've reached that normal operating mode, we're pretty confident that things are configured correctly. Passing that routine indicates that we're able to generate 120 volts at 60 Hz without being overloaded or putting users at risk. If our soft start fail counter exceeds a set threshold, in this case 4, we'll no longer attempt that soft start sequence until a reset pulse is set to the inverter microcontroller. We're pretty strict about this. I know it's a little aggressive, but it's possible that we just shocked somebody 4 times, and I'd really rather stop. While it's annoying to have a UPS turn off when unnecessary, I'd rather be inconvenienced than dead. Don't you see? It's the little things. Only shocking somebody 4 times is just one of those little features that might not exist on a commercial UPS. Doesn't that just warm your heart? It's that genuine care that warms my heart, like, homemade pie. Just doesn't get better than this. We implemented these features in the same firmware class responsible for achieving voltage regulation. You've seen what this looks like in software, and here's how this looks on the bench. I've set the trip thresholds we've been talking about to values achievable with small loads to keep things within the output power currently possible with our UPS. Ultimately, these limits will need to be adjusted as we dial in the output power of our UPS. That won't be too difficult though, because it's defined in our header file as a pound-define. The flexibility that we've just added allows us to demonstrate the various protective functions of the UPS at a low power level, like right now, or tweak things down the road if we want to change output voltage, amplitude, or power level later. So let's check out the soft start routine first while this is unloaded. Hey, that looks pretty good. How does that look when we actually add some load though? Is this going to behave any differently? No, that still looks pretty good. Okay, what about a bigger challenge? How does this soft start routine look when connected to a load that the power stage can handle, but more than the output power threshold we've defined in software? Whoa, check this out. We made it through the first soft start phase, which makes sense, but then we fail at that second stage of the... Wow. Our UPS responded really fast. Rather than browning out, the UPS cut out only 60 milliseconds after turning on, rising to 75 volts RMS before detecting the fault. Now I'd like to exercise the hiccup overcurrent protection routine once or twice. It's, well, simple in theory, this is actually more difficult than it might seem. What we need to generate is a transient overload that can produce a current spike large enough to trip the OCP, but only for a very short time. And if we trip the overcurrent protection 4 times in a row, our power supply will give up and require a hard reset. Ironically, the best way for me to trip this hiccup overcurrent mode routine is using inrush current, which is the thing that our soft start whatever. I'm gonna try and hot plug some devices into our power strip that we've plugged into the UPS and see if we can get that overcurrent, that hiccup mode overcurrent protection to activate. After many power cycles, I managed to flip the power strip and sync with the peak if a sine wave, and this tripped the overcurrent protection due to the inrush current into the 2 LED light bulbs and the phone charger. Notice how there's a couple seconds of off time right after we flip this on and trip the current limit? Now, that's longer than I'd like to see, which is the main reason why I'd like to have a push-pull converter and inverter soft start at the same time. We could cut this transition time in half, but it becomes less obvious which current limit caused the OCP to trip, so for debugging purposes, that's why we did it this way. But in the long run, I'm guessing that's what the fancy display was for. Error codes. Right. One more thing, tangentially related, you may have noticed that the power readout has been displaying 999 watts for a while, but it's fixed now. Turns out we accidentally crossed a wire in software and we're reporting the average current as the same magnitude as the voltage. Whoops. Turns out we were calculating the average current using the voltage buffer. Simple mistake. After correcting this error and using the right buffer, decided to change the current to be passed in milliamps instead of amps to use the variable better. We're now able to report and display voltage, current, and power information at a much higher level. It's both really neat to be able to watch the UPS and kilowatt meter measure and display output power in real time, but it's also critical. This power number is displaying the voltage and current present on the output as measured by the UPS. If the power reported is wrong, that means that either voltage or current measurement is incorrect. Since we know the voltage measurement is correct, that means that power being accurate means that the UPS can measure output current accurately. There isn't much sense in testing overcurrent protection if one can't verify that the UPS is able to measure current. Yeah, so we just made sure that the UPS could measure current first and then moved on with our testing. We've successfully demonstrated that overcurrent protection and soft start routines of our UPS are working well. Now that I've seen these features work at this low power level, I've got some serious confidence that they will continue to work at higher power levels as needed. We're still limited to around 100 watts of output power. That's due to a combination of design defects that we've been uncovering, but I'm cooking up a plan to get this UPS where I want it to be. We're almost done testing this UPS, but there is still a lot of work to do. So subscribe if you'd like to be notified of our future videos. We will be testing our battery charger circuit and testing some high-level UPS functions, like crossing over between the primary and secondary DC inputs. We've got some really exciting stuff coming up. I think that overcurrent protection is great. If you think so too, let me know by hitting the like button on this video, showing us what you're up to on Twitter, or letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!